Thank you very much for being here, everyone. This talk will be about wireless access for URLLC. As Chet already mentioned, the requirements for URLLC are quite stringent, both in latency and reliability. So through this talk, I will try to explain some of the techniques that we can use and the different options that we have to achieve URLLC for the wireless access. I divided this talk into some sub-chapters that kind of increase in complexity. We have first an introduction of what URLLC is and how can we see it from the wireless access perspective. And then we have a single user scenario that we can have one-to-one communication. We have the downlink, and then we have the uplink. And finally, I will give some of the conclusions. So first, what is URLLC? Chad already mentioned that we have some general requirements stated by the 3GPP. For example, 1 millisecond latency, user plane in the uplink and downlink, and a reliability of 1 minus 10 to the minus 5 or 0.9999. And we usually, as he already mentioned also, is that we observe traditional latency functions more or less like the one that I'm showing here. I will just try to get this. So first they look quite in general. Yes, that's because normally we see it in the sense that we have many access opportunities or channel uses to achieve our goal. The latency reliability function refers to the fact that it's the CDF of latency when we look at the rectangle that he mentioned already. So we have a specific rectangle in the plot that we're going to focus on because we have a deadline. We have a target error probability that is quite low. And we have to fit in there. Everything that we do outside of this rectangle is not relevant for the URLLC system from their perspective. So as I already mentioned, this is the traditional latency reliability function that we can observe. Instead, URLLC, as we mentioned, we know, is characterized by few channel uses. Why? We don't have many opportunities to transmit and fail. For example, in 5G, we have that mini slots can be of around 0.1 to 5 milliseconds of length. We have the random access that in the new standardization has been reduced to 0.5 milliseconds. So you have one access opportunity per each physical resource block. So 2 per slot that subframe that we know before. And we have this milliseconds or few milliseconds deadline. So what we have is normally a step function. I cannot see my pointer anymore, so okay. We have the step function that is shown in the graph usually. So basically we have some channel uses. We have to provide the reliability guarantees within those channel uses. But not only the channel use counts toward this, so it's not only transmission what we're talking about, it's also the waiting time. Why? Because if we have resources that at widely spaced in time, the waiting time can be quite large compared to the transmission time. So we need two components here. We have a transmission time that includes potential retransmissions or replicas. We have the waiting time, that is how much I have to wait from the point in time that I want to transmit or that I get the packet and that I get a chance to transmit or that I can use the channel by itself. So this is the tricky part. Here I'm showing, for example, that you have 3-4 channel uses. That should be typical. So we should do the best we can with what is given.
Israel, if you're using PowerPoint, you may right-click and see you can select pointer options, laser pointer, to see if you can recreate your.
Okay, the thing is that this is PDF.
Okay, then.
Yes, I could see my pointer from the beginning. I cannot see it anymore. Ah, there it is. Hopefully you can see it again. Not anymore. Okay.
Yeah, well, your hand was back for a short while.
Yes, just forget about it. I will try to explain with words. It's fine. Thank you. Okay, Then we go to start with the single user scenario. So we have this guy that wants to communicate with the girl, and it's one-to-one. So basically all the channel is for him. We will have a waiting time, we will have the transmission time, and we will have the propagation delay. Propagation delay in terrestrial networks is quite short, a few kilometers. Speed of light should not be that of a contributing factor. But as Beatrice will explain later today, this is important for satellite networks. And I have to say that even in terrestrial networks, in tactile internet scenarios, this propagation delay becomes a problem. Why? Because the usual examples are I'm a doctor that is in the UK and I want to perform surgery in a patient that is in the US. So the distance is quite long. Even if we travel at light speed, this propagation delay can become a problem. But since this is URLLC and we're going to give some insights on how to achieve it, I will neglect this part and basically focus on the central part, that is transmission time. I have to say that even this simple single user scenario, when looking only at the transmission time, is complicated. Why? Because there are many variables that we can have. We have different modulation encoding schemes. Higher order modulations, of course, will give you a higher data rate to transmit your, for example, 32 bits, 32 bytes, but are less reliable, so more prone to errors. Lower modulation encoding schemes are more robust, but of course you need more time or more symbols to transmit. Bandwidth is also an essential part of this, and I exemplify with the two figures that we have here. These were taken for example, an orthogonal frequency division multiplexing channel. In the left part, we have one that has 12 subcarriers in the frequency domain and 7 symbols in the time domain. This will be a traditional physical resource block in 5G, 4G. And on the right, we have basically the same resource block, but with half of the frequency and double the symbols in time. These two are quite not the same when we are talking about URLLC, because if we have more symbols in frequency, then we can transmit more data with less time. That is highly valuable here. We were talking about 4-channel uses or 3-channel uses to get information there at most, or even less. So we have to do the best that we can with what we're given. But this also means that we will try to increase the frequency or the channel bandwidth as much as possible so we can transmit in the shortest time as possible. So the big question here is how much bandwidth can you afford? And how much of it are you willing to waste? If you have only one user that is active 1 out of 100 time slots and you have a really wide bandwidth, then you're wasting a huge amount of resources. You would like to reduce it, of course, by reducing the bandwidth of the channel, so the resource utilization is higher, but of course you're increasing your transmission time. This is what if you could see the summary of this talk, this is what a trade-off between naive over-provisioning. So if you don't know that much of the channel, the best that you can do is get the best that you can for the money, right? You don't know what you're going to use it for, so just pay for it and get the best that you can. Hopefully there will be some techniques and some options to get the most out of what we can afford, really, and not go overboard with this naive over provisioning. So I heard that you already had Peter's talk about learning and probably approximately correct measures, basically. So the key to not over provision is to learn the channel or learn the system. But the key question here is that we have to answer is what is the level of knowledge that we require to provide URLLC guarantees? I will raise another question and say, what is the level of knowledge required so the effort in learning pays off? What can we do if we don't know nothing about the channel? What can we do if we know something about the channel using simple techniques? What can we do if we know a little bit more of the channel when we use machine learning? for example? Well, the thing is that there are a lot of factors in play. For example, what are our hypotheses? If we're using machine learning or just simply some maximum likelihood estimator, how many samples do we need? And a very big question here is, are these samples representative? Here I'm going to use this turkey that I have and provide an example. So let's say that based on personal experience, this poor turkey will never know what will happen on that fated day of Christmas or Thanksgiving, because he will not experience that through a long period. It can be years and he will never know, unless we can give him some prior knowledge about it. But we need some prior knowledge about noise, coherence time, path loss, and many, many factors. So this is a very complicated task. And basically, this takes us into notions of non-linearity and consistency. I already mentioned that by experience, this turkey will never know what will happen. But if we give him some prior knowledge, then we can do something about it, right? But the thing is that this goes into the line of structural risk minimization instead of empirical risk minimization. So we need some prior knowledge to have a wider view of the system. And if we aim for consistency, we will reach the point that the sample size that this turkey will need depends on the hypothesis that we have, or the hypothesis set, and the distribution of the samples. The example of the turkey again goes in the sense that what he observed are not IID distributed samples. So he can observe one day after the other, but he will never observe the day that matters, unless we give him the prior knowledge. I think this is enough for learning. You really have a lot of in Peter's talk, and this is just to exemplify and raise some ideas on what do we need to provide URLLC guarantees. If we don't know the channel, if we don't know the system, what can we say about it? But this is complicated, so we will start with some specific scenarios and some specific approaches to URLLC. So one of the big questions here is, what should we use if we can perform several transmissions for a single packet? Should we use replicas, or should we use feedback to perform retransmissions? If we use replicas, we have this waiting time, and then we'll just simply take our packet that we want to deliver quickly and transmit it, for example, 3 times in the figure. So we have the transmission time 3 times in our timeline, and for an erasure probability epsilon, the number of replicas n that we would fix beforehand, we can have a probability of failure equal to epsilon to the power of n. Again, this is if you know the parameters. But for example, we can play with some upper bounds for epsilon, right? Saying that your system usually has an epsilon of 0.1 or less would be a good guess for starters. On the other hand, for feedback, we have the same waiting time. We have a transmission from the guy to the girl. And then we have the option to add some feedback. This will be usually shorter, transmitted over a channel. Normally, this is assumed to be perfect and to have a separate channel. But for URLLC, well, we have to be realistic about it, right? So we have this in time here. Of course, the feedback cannot come before the transmission is finished. So basically, he transmits, waits for feedback that the transmission was received. If not, he will transmit again. And we'll just follow this process until success or until the deadline is exceeded. So basically, we see that feedback will give you the same reliability with the same channel uses, but the thing is that adding this part of the feedback leads to less possible attempts. So basically, you're stretching your transmission time because of feedback a little bit. one of the advantages of feedback and retransmissions compared to replicas is that this increases the time diversity. So we don't know the coherence time of the channel. The coherence time of the channel, when we're talking of such short transmissions, may be around the same scale than our transmission. So replicas can be, for example, prone to burst errors. Feedback, well, gives you a little bit more of time diversity. But as I said, if you don't know the channel, you don't know what really you should use. So we will move away from this simple yet complicated first example, and you will move into URLLC in the downlink. Here we have some options to achieve diversity that will help us get better results, and some of these are power allocation. We can exploit path diversity and spatial reuser multiplexing. And since we have now more users than before, we're not only one, we can do some kind of collaborative learning. So this will give you, I will give you some ideas in this line only. We will not go that deep. So power allocation. Power allocation, as Chedomir already mentioned, has been investigated for heterogeneous services. This goes into the line of orthogonal or non-orthogonal resource allocation. And one example is given in this paper, which is quite illustrative. So basically you have your 5G system or any system that has some bandwidth, has some time slots, and broadband users will be transmitting, will be receiving packets in those time slots most of the time, for example. So resources are not pre-allocated to the URLLC users. Instead, when they want to transmit, as you can see in the figure of the left, they can, well, when they want to receive, when the base station wants to transmit to these URLLC users, he will follow one of two approaches. One is puncturing and the other one is superposition. Puncturing here refers to the fact that the power for the MBB user at some point will be 0. And instead, this transmission or this part of transmission will be replaced by a URLLC traffic for a specific user. So power 0 for broadband, some power relatively high for the URLLC user. And superposition is similar, just in the sense that the power for the MBB user is not 0. So you have some power that could potentially be used for joint decoding or successful interference cancellation. And yeah, this paper also attacks the fact that you don't want to give that many resources to the URLLC users because they are intermittent, short packets. You don't want to waste resources, but you want to minimize the latency. And you can do it just by scheduling them in the next mini slot in this case. As this is downlink, this is possible. So the base station itself gets the traffic and schedules it. So he has the with this. And one of the big questions here is how is the broadband traffic affected by this puncturing or superposition? This paper is quite general and employs some functions, linear function, convex models, and a threshold-based model to assess the losses. And I would recommend a read to this one. Yes. What these different functions illustrate is how the MBB traffic is transmitted. Are they using some coding, erasure codes? Is it just that they are interested in specific packets? Do they have in order delivery, for example? That would be the threshold model. If you don't get the packets in order, then you will not decode until later, probably depending on the system design. Another way of achieving this, now that we have seen power allocation, is through path diversity and spatial reuse. So this paper proposes the use of short-range communication in clusters. So this paper, as Chedomir also already mentioned, and not all of them are really doing URLLC. Some of them are doing URC, for example. Some are doing low latency. Well, this is well branded as ultra reliable communications. And what they are doing with path diversity is that we have a base station transmitting the downlink in an industrial scenario. So basically he wants to broadcast information, control information to the actuators that are in the factory, for example. He broadcasts information in a segmented manner, so 3 or 4 or 5 packets. And then the users that get some of the packets will retransmit them in using, for example, short-range communication or some other techniques, low power, to nearby devices. So this is adding to this path diversity. The thing is that when we see this kind of approaches, the difficult part is not how to initially design them to see some gains, but how to design them in the practical aspect, because the challenge is coordination. This is taken to opportunistic routing, where you try to exploit the broadcast nature of the channel to find alternate paths and not just follow a single path in routing. Well, but this is more or less the same for two-hop communication, but as I mentioned, coordination is difficult because then we have multiple access in the clusters. And finally, for path diversity, also the Peter has a paper in wireless ultra reliable low latency communications, and they emphasize the importance of massive multiple input, multiple output, massive MIMO, and the use of beamforming. This will allow you to have high SNR and spatial multiplexing. So basically, instead of broadcasting the information, you're giving targeted separate channels just due to spatial multiplexing. And this is essential, again, for Industry 4.0 scenarios where you have a high density of deployment, high density of actuators and sensors. And yeah, this paper explains some techniques to achieve some gains with path diversity. Now, just to conclude the part with the downlink, I will raise again this topic of learning, and specifically collaborative learning. We can have transfer learning, federated learning, distributed learning, or simply send information for a centralized learning. And this apparently should solve the problem of our turkey, right? If he talks to another turkeys, then he can get this prior information, he can know what to expect. But the thing is that we want to have sufficient diversity in sense of experiences. So turkeys that are a little bit older, a little bit younger, and not groups of turkeys that know exactly the same, that they are highly correlated. So even in this scenario where we have multiple agents and we can have different types of learning, having the correct training data can be tricky. This learning can also apply not only to learning the channel, but learning the activation of the user. So this figure also helps me to kind of describe that if you have sufficient diversity in terms of activation patterns and times of activation, then probably your system will be fine in a multiple access scenario. But if correlation is too high, you need to know this to design the system accordingly. You have to decorrelate the users to assign the resources. You don't want all of them active in the exact same time slot, for example. So we're moving to the, let's say, interest that is the URLLC in the uplink. Here we're going to go through 3 main points. That is Groundbased random access versus Groundfree random access. These are the 2 big general bins where you can put access protocols. Then we will have feedback and replicas that are relevant also for this random access, but also for users that are already connected to the network. How do you assign the resources? And this will lead us to multiple access and slicing techniques. First, I will talk about Ground-based versus Ground-free random access. Well, I have to say that first, the 3GPP has adopted Ground-based random access as the de facto for 5G, 4G, narrowband IoT, LTM, everything is Ground-based random access. And this works like this. From the base station, you have some system information and synchronization that's sent to the user equipments. Then they will wait for a slot to transmit. They will send an access request. This access request, well, you have different mechanisms, adoption sequences or orthogonal frequency hopping patterns for narrowband IoT that needs some processing. After this processing at the base station, so basically the coding, you need to send a grant to the users. So basically the access request has no information of the users. They are only asking for connection. the base station, then we send the grant to those who succeeded, some more processing, and then more signaling and concluding the handshakes. The interesting part about grant-based random access and why it has been so widely used is that LTE and previous systems were designed for broadband traffic or simply calls. And grant-based random access is quite good to transmit long packets. Yes, it has a big overhead in general. It requires some processing. Access failures can cost some time. But if you're going to transmit long packets or being connected for a long period, then this will pay off in the end, because then you will have a connection. This is the only way to go into a connected state. Then you will have some resources allocated for you. That's quite fine. One of the big, let's say, arguments in the research community of grant-based random access is what happens. Do we have a capture effect? Is it beneficial? Here, the capture effect refers to having several access requests transmitted by the same user, and the base station can decode them. So it gets tricky what to do with them after this. So compared to grant-free random access, we can see that we need some system information and synchronization. Then when we have a slot, we will transmit the packet. We have probably some processing, and if we want to have it, some feedback, or we just simply replicate the packet. I will talk. The benefits of grant-free random access is that it's simple. It's best for short and infrequent transmissions. So basically, you will be willing to go through this process several times a day, for example, if you're only going to transmit 32 bytes. So it sounds good for URLLC. The challenge is with correlated activations. Anyway, we may need some kind of coordination from the base station or among the users to avoid failures. Capture in this case is quite beneficial because then you're decoding the packet actually, not just an access request. So this is saving a lot of time. So capture is an important element in the rest of the talk for today. As I mentioned, we need feedback. Maybe, yes. How much feedback do we need? We need ternary feedback, received, not received, or received, or yes, or empty slot, for example. There are approaches from the 1980s on Bayesian estimation on transmission probabilities that use this ternary feedback quite well. So the first point that I want to tackle is replicas versus feedback in the uplink. So we have this paper that precisely was dealing with a random access in 3GPP networks. And the benefit of using replicas here is that they can be combined to increase the SNR. So basically you're transmitting exactly the same. And since your channel won't change that much from one transmission to the other, they are back-to-back transmissions, then you can add them coherently, basically. So you increase the SNR. So this paper shows basically the regions between reliability of retransmissions and reliability of replicas, which is always higher than retransmission because of this incoherent sum of the SNR. And they show some regions where repetition is better, repetition is replicas, and retransmissions are better, depending on the type of channel and on the reliability. So there are quite some trade-offs. This figure is for 2 replicas or 2 retransmissions. They also observe that if you increase naively the number of replicas, retransmission starts getting better. Why? Because you're limiting the maximum number of retransmissions. You're not just wasting 16 transmission slots for your replicas without knowing what will happen afterwards. So they are also considering the cost of a transmission. And now we will move on to some random access protocols. Now we will talk about replicas. So we want to basically look a little bit more into the multi-user case. So the de facto protocols are most of the time multi-channel slot Aloha. Why? Because it's quite simple, it's quite flexible. Users don't really need that much of coordination. So basically you need to know the frequency, the time, or how the channel is configured. And then you will transmit. The example that I'm giving here is for a case where we have 3 users. They are transmitting in every slot. You have 12 frequency bands that you can choose from. And we can see that the collisions occur when 2 users select the same resource to transmit. As I mentioned, they can be frequency, they can be randomly selected orthogonal codes, as in 5G with this set of 2 sequences. So can be a lot of things. A lot of resources can be used for this. As I mentioned, this is quite flexible, so we do not need that much information from the base station, but we have other options, right? For multiple access, yes, we have, but they require a connection or more fine-grained coordination. For example, we have time division, multiple access, frequency division, multiple access, and code division, multiple access that normally they require signaling from the base station to allocate the resources. So these are mostly for the connected mode. And what happens if our activations are quite sparse? Well, what will happen is that we're wasting resources. We assign, for example, time slots to a user that is active 1 out of 200. Well, we have to assign them, right? Because they have to be frequent, so your latency is quite low. With code division multiple access here, I have a question mark because we have also asynchronous and basically non-orthogonal codes that can be used and have proven to be quite useful. So looking more deeply into the multi-channel slotted aloha, why don't we use this, or what are the drawbacks when using this approach for URLLC? Well, here I have a plot where we have our orthogonal channels. So basically it's for the 5G random access channels. And the equation that I have there gives you the expected number of successful accesses. X is the number of active users. The black line, the black straight line, illustrates the case where we have infinite number of resources. So if you have infinite, the expected number of successful accesses is just the number of users per time slot. But as we can see with the plots, having just 5 users, 10 users, even though when you have 4 resources, the probability of success is not high. We have some users failing in the access, and in this case, what will happen is that we will need some retransmissions that in turn will sum up with the active users from the first time, and this will create a snowball effect that causes a lot of problems for these slotted aloha and retransmission based channels and protocols. More clearly illustrated, the probability of collision is the equation that I have there, and we can observe it in the plot. We can see that if we have 40 resources and 10 users, that's quite a big over provisioning. Then we're having 20% of collision probability, which is quite high. So maybe we should look to some other alternatives and more intelligent protocols instead of simple multi-channel slotted aloha. And one of these alternatives is irregular repetition slotted aloha. Here we will transmit replicas. So instead of just retransmission based, we will use replicas that I already mentioned that are quite beneficial because you transmit several times at the beginning. You don't wait for feedback. Since you have several transmissions instead of one, this helps with the erasure probability, so it's quite fine. And the example that I'm giving here is again for 3 users, a frame of 4 slots. So basically the row that we have at the bottom that says BS, the base station, is the actual channel, and the user 1, user 2, user 3 are the activations of the users. With IRSA, what you will do is you draw a random number of repetitions. You draw random numbers to allocate them in the frame, and you simply transmit exactly the same. These are replicas. And the base station, what it will do is that it will collect what was received in each of the slots. If we have singleton slots like the purple and green one, slot 3 and 4, then he can decode, and then he can perform successive interference cancellation to remove the contribution of interference to previous slots. So in this case, even though user 2 collides twice with user 1, the base station will be able to decode that packet. And the benefits of IRSA increase dramatically if we can consider capture. If we consider capture, for example, user 1 and user 2 may be decoded from the first slot, not until the third slot that we have here. The downside is that packets that arrive in the middle of the frame should be pushed to the next one. And we have to take into account the design of the frame because, of course, the load is determined by the number of users and the number of replicas that they can transmit and the length of the frame. So there are specific regions where each side is quite beneficial, but have to be selected carefully. Some more research should be done here. And especially some research is lacking in the sense that not always we assume or we consider erasure probabilities, because this is a quite complicated protocol to analyze mathematically. We use graph theory, we use some advanced techniques, but usually resort to using some bounds for it, even when we don't have erasure probability. So this is quite complex. Another thing that we can do, but this is more for the connected state that I described before, with orthogonal multiple access, is basically TDMA with the broadband user. So here we're considering heterogeneous services. For OMA, we will have broadband user active in some slots using some erasure coding, and we will do TDMA basically with the URLLC users. Of course, if this is URLLC, we have to schedule them quite frequently in this figure, once every 4 slots. So basically we're having some broadband traffic with potentially some URLLC traffic if our channel uses are sufficiently large. We're going to compare this to non-orthogonal multiple access, or NOMA, that has several benefits in this case. As I mentioned, OMA is for connection-based services. So basically you have to synchronize, you have to have resources allocated to you as broadband, as URLLC user. But if we use non-orthogonal multiple access, we can have some resources for the broadband user that the URLLC users can also use. So these are called mixed slots in the figure. In this sense, it's immediate to see that NOMA may be better for URLLC. If I can transmit whenever I want in the frame and be decoded immediately, then this is quite good, right? It's like puncturing, but from the uplink. And also, it minimizes resource wastage because we're not assigning slots to users that may not use them. And as I mentioned, also the capture effect and possibly joint decoding are quite beneficial. So what's the catch here? The catch here is that, of course, we rely on the capture effect for this to be beneficial, or on the lack of activation of the broadband user. Some work that we have done focuses on a simple collision channel model, where if we have transmission from the broadband user and from the intermittent user, you will cause a collision, and you will only recover if the broadband user is decoded and can remove the interference to the URLLC user. This plot is quite intense to explain. So this is a Pareto frontier. The Pareto frontier, I would like to have the pointer now, but the Pareto frontier, what it means is that you generate a lot of points for different configurations and values and settings, and you plot them in a 2D plane. Then you look at the KPIs that you're aiming for, in this case, throughput for the broadband user. We want the highest possible here. And we want the latency reliability for the intermittent or URLLC user to be as low as possible. So in the graph, this takes us to the lower rightmost corner. So the closest you are to a high throughput, in this case around 0.8, and a low latency reliability, in this case the 90th percentile, the better you're doing. So observe to the points that are to the rightmost and lowest corner of the graph. All the rest of the points lie in an area that is above or to the left of those points for each of the schemes that we're considering here. So we have OMA with some queuing. So basically, since the URLLC user is not able to transmit at each time slot. What he has to do is to queue some packets, so he won't drop them. If we don't queue, the performance is quite low because the maximum throughput that we can achieve for the broadband user is not that great. And compared to NOMA and OMA with queuing, the latency is way higher. Then we have OMA with queuing. This quite increases the throughput of the broadband user. Why? Because we're still achieving this 90th percentile of latency reliability, non-infinite. So we have at least a reliability of 90% here for the intermittent or URLLC user. And with NOMA, we can see that we have some regions where it performs quite well. If we look at the lower part of the graph, near to the 0.2 in throughput, we can see that it's basically the same and arguably a little bit better than orthogonal multiple access. And also, if we look at the highest possible throughput, we can see that NOMA achieves it with slightly lower latency reliability. Of course, since this is URLLC, we focus on the former case. So we can see that even though we're considering the worst case for NOMA, because all the collisions cannot be decoded, we can have some gains with it for URLLC. So this is quite interesting. And yeah, basically this concludes the talk. I will just give some conclusions on this fact. So basically, diversity is key. We have diversity in time, space, frequency, power. Jimmy will talk about diversity in interface diversity or multiple radio access technologies, multi-connectivity. This is quite interesting case. And we also talk that URLLC guarantees depend on the level of knowledge. How much you know will allow you to give an estimate of what will be your performance. Of course, you can always restore to bounds, but at least you have to know that the parameters of the system fall within the parameters that you consider for these bounds. Also, we saw that grant-free access is preferred unless you're going to connect or unless you want to maintain the connection. So if you're transmitting quite frequently, probably it's better to just maintain the connection. If you're going to transmit once a day, grant-free access is fine. Twice a day, 10 times. But if you're going to transmit 1,000 times a day, probably just staying connected is the best because you have dedicated resources. But we also observe that non-orthogonal multiple access can help us with this aspect, having non-connection state for the URLLC user and still achieving really low latency reliability. Aloha is simple, but we can do much better. Replicas and other schemes would be beneficial, but we need to know the coherence time. And even we should know the frequency, the coherence in frequency for the channel. So not always transmitting in the whole bandwidth will be beneficial. Finally, as I mentioned, non-orthogonal slicing and NOMA access are promising under some appropriate conditions. But also, even in the worst case, we can see some gains. So this is quite interesting, and we should continue this line. And this is the end of my talk. Thank you very much for your attention.
So, do we have any questions for Israel?
Or can I, because I don't know if you're there.
Yes, I'm here, and I have a question.
Yeah, here.
Okay.
In this field of multiple access channel, what's the possibility of applying machine learning to come up with to learn codes, like in the you were talking about these repetition codes that are used to then decode the message, and yeah, there are some optimality already there that can be shown to be an upper bound, or there is the possibility of using machine learning to possibly optimize the schemes and further enhance the final performance.
Yes. Okay. Well, that's a very good question, because one of the utilities of machine learning is that it provides an extension to when we cannot do the analysis by hand anymore. So basically, you sometimes reach to these very complex systems where just doing the analysis is quite complicated. And of course, all of the models that you use are wrong, but they should be sufficiently rich to be useful for your application or for your use case. Sometimes just for the sake of arriving to a closed form expression or some formulas, we end up simplifying the models quite much. And in the end, the conclusions that we can get are not as expected, or they could even overemphasize or underemphasize the benefits of what you're doing. So machine learning in this case provides us some tools to have much richer models, use them as an input to the learner, and the learner can just simply try some simple things or even complex mechanisms to arrive to, for example, a channel configuration, a system configuration. I have been doing this because with these OMA or NOMA schemes, the calculations are quite complex. And if I wanted to, for example, find the configuration that is optimal for an activation probability of the URLLC user, this takes, if I just do a brute force search, or it will take days. It has taken some weeks now, and my laptop in the university is still running for some values. And of course, as the derivations are so complex, we cannot optimize them by hand. So in this case, what I have resorted to do is some simple hill climbing or simple techniques. Of course, you can do much better with some more robust learning. And some important aspect here is that normally we observe a system from fixed parameters. So we know the parameters. We know epsilon, we know the activation probability, we know the coherence times, we know the noise, we know quite a lot of things. But the system should learn some of this, right? So we can probably optimize to these fixed values, but what happens if the values are slightly different? If we can do this by hand, doing some convex optimization, then we can have the expression for example, all the values of the activation probability. But if we are doing some kind of search, this is complicated, because in the end, the system observes them in long periods. For example, a URLLC user that activates once per day, well, it will take you quite some time to characterize its activation, right? Quite some days even, to know that he's activating once per day. That's fine. Now I know, after 1 month, I know the activation probability, so now I can work with it. So some machine learning techniques can be used for this, to speed up the process, for example.
I have a question, which is, I think, continuation of what Matteo asked about learning codes. Like you showed IRSA, and there are more general codes now, like in the same line of work for random access. Like, for example, especially for random access, like can machine learning be a tool, or it's just increases more complexity in the network? Because these codes or can machine learning be helpful to learn better codes than these?
Yes, this was in the line that I mentioned. Probably my answer was just quite extensive. Yes, if you know some of the parameters that you're dealing with, how's the system, then you can decide, for example, some specific would be for IRSA, you could design the number of repetitions, the frame length, even you can add more channels or restrict the access or do some more advanced techniques. But of course, the utility of this depends on how rich your model is. If you want to do this by hand, some optimization, then you have to do some very simple things. That's why I mentioned that erasure is not always considered in IRSA schemes. If you use machine learning to design the scheme, so to select the parameters of the scheme, that you can do probably better. You just need to use the correct machine learning tool for it.
Okay, good. Thank you so much.